Okay, so today's video is going to focus on binomials and binomial distributions. So we're going to go through and we're going to be looking at these examples and using them to kind of work through this information. And these examples will be your notes. So looking at our first one here, in 2005, Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, Memphis' Darius Washington attempted a three-pointer. He missed but was fouled and went to the line for 3 free throws. Each made free throw is worth 1 point. Was it smart to foul? So we can determine this by looking at probabilities. So if we look at our first question here, what are all the possible ways the shots could fail? I'm going to go ahead and make be a check, misses be X's, so that we can save a little space here. So one possible way that the shots could go, right, is that he could make all 3 shots. A second possibility, right, he could make 2, miss 1. He could make the first one, miss the second one, make the third one, so still make 2. Okay, he could also miss the first one, make 2, make the last 2. Okay, he also could make 1 shot and then miss the others. So he could make his first shot, miss the next 2. He could miss his first shot, make his second shot, miss his third shot. He could miss the first 2 and then come in and make the third one. Or he could end up missing all of them. So these are all of my possible combinations that could have happened here at the end of the game. So the information it gives us here with number 2 is that he was a 72% free throw shooter. So find the probability that Memphis will win, lose, or go to overtime. If it's tied, they'll send it to overtime. So when we found the probabilities, we'll go ahead and we'll put them on our table here. So looking at our different combinations up here, there's only one way that Memphis can win in regulation, right? And that would be if he makes all 3 free throws. So we need all of those things to happen at the same time, right? So that is going to be our 0.72. Those are all independent of one another, right? 1 free throw doesn't affect his next free throw. So the probability he makes them is every time is 0.72, right? Which is also the same as writing 0.72 to the third, right? And so when we plug that into our calculator, we get a 0.373 probability that they'll win. The probability that they will lose, okay, there's a couple scenarios of where they will lose. He could have 3 misses, so that would make them lose. So that would be 0.28 is his probability that he'll miss, right? 1 minus 0.72 gives me that 0.28. Okay, so if he got 3 misses, same as getting 3 makes, I need all of those to happen at the same time, right? Again, that's equivalent to 0.28 to the third, okay, which would give us 0.022. They would also lose if he had 1 make and 2 misses, and it doesn't matter the order, right? So if he had 1 make, that would be 0.72, and 2 misses and 2 misses, or second miss, right? So that gives us 0.056. But if we come back up to the top here, there are multiple ways that this could happen, right? There's one way this could happen here. Here's another way this could happen. Here's a third way this could happen. So I'm really either adding all those together, right? Because it's an or. I could do it this way, or this way, or this way, right? Adding those 3 things together is the same as saying 0.56 times 3, because I have 3 ways that could happen, which gives me a 0.0169 probability here. So our third option here is that it gets sent to overtime. So to get sent to overtime means I need to end in a tie. So that means I need 2 makes and a miss, again, regardless of order. So a make would be a 0.72. Another 0.72 probability, because again, they're independent of one another, with a final miss at 0.28. Okay, this gives us a 0.145 probability. But again, if we come back up here, there are 1, 2, 3 different ways that this could happen. So again, I can add 0.145 plus 0.145 plus 0.145, or just multiply that times 3, which gives me 0.433 5. And there's a calculator, there's a formula we can plug this into and use on our calculator that I'll show you in just a few minutes. I don't want to freak you out yet. Okay, so you'll notice there that it says prior to watching each shot. So I'm not going to cut in video of each shot or anything. I'll just tell you what happens. Calculate the probability that Memphis wins the game in regulation, loses the game in regulation, or sends the game into overtime. So here's their initial score here before we started, 75 to 73. So the probability that Memphis is going to win, well, that's his probability that he makes all three. He hasn't taken any of them yet. So his probability he makes all three would be 0.373. The probability that Memphis is going to lose. Okay? Well, again, he hasn't taken any of the three yet. He had two ways that he could lose, right? He could miss all three, or you notice I said or, and then I wrote an addition sign, or he could miss two of them and make only one of them. So the probability right now that they'll lose is 0.191. And the probability they send it to overtime is the probability that they end up with that tie. Okay, which is he makes it twice and misses once. So he goes and he takes one of the shots and he makes it. Right, so now they're at 75, 74. So now the probability that they win, well, he's got to make two more shots. Right, so now they're at an over 51% chance that they're going to win now. Right, the probability that they completely lose, he's got to miss both shots that he's about to take now. So there we go at 0.0789. And then the probability that's in it overtime, he can make one, miss one. All right. And again, there's two ways that he could do that, right? He could make one, miss one. He could miss one, make one. So that gives me that probability there that it happens times the two scenarios. Gives me 0.4032. So it's looking pretty good right now for Memphis. So now he takes this shot here and he misses. So they're still sitting at 74, 75, and he has one shot left. So the probability they're going to win right now is 0. Okay? Best they can do is tie it. Okay? They could lose, meaning he could miss it and they stay, and they lose, and they could win, or go to overtime at least, and possibly win in overtime, 0.72. Okay, and guess what happened? They lose. He did not make it. They end up losing 75 to 74. Okay, so let's look at what we've got here with this second set of information here. That Darius Washington was a 40% three-point shooter. So do you think Louisville was smart to foul? Okay. So we've got a couple of options that could happen here, right? If they did not foul. So I'm going to come over here on the side. So no foul for Louisville. Okay. If they had no foul, then Memphis has a 40% chance of winning because he's a 40% three-point shooter. So there's a 40% chance that he's going to make that shot if they don't foul him. If they do foul him, so let's come over to this other side and talk about what happens if they foul him. If they do foul him, there's a couple scenarios, right? He's got to make all three, which is only a 37.3% chance, so that they'll win in regulation. However, you run the risk of them going to overtime, and that was a 0.435 or 43.5% chance that he'd send him to overtime. So either winning in regulation and or sending it to overtime was a 77% chance. So it's kind of close, right, to outright win. They're about the same with the foul versus the no foul. But when you take into the overtime consideration, the foul actually may have been a little bit risky. All right, so let's look at our big takeaways here. So our takeaways here are for things to qualify as a binomial random condition, a binomial random variable. They have to meet certain conditions. And I'm just going to come out here so I can write a little bit bigger. I don't have my super nice computer with me, so my writing is a little messy again. All right, so the conditions for it to be considered a binomial random variable is it needs to meet what's called the binary condition. So each individual trial needs a success or a failure. And in our basketball example, that's pretty easy to see, right? He makes the free throw. He does not make the free throw. So a success makes the basket. A failure, he did not make the basket. Okay. Again, remember, these are your notes, so add what you need. Okay. They need to be independent of one another. And I can't spell. Let's start over. So each trial is going to need to be independent of the one before it. So again, each trial needs to be independent of the trial that happened before it. There needs to be a set number of trials. For instance, in our basketball example, he had 3 trials, and that is written as lowercase n equals whatever it equals. So again, our basketball example, it equaled 3. And there needs to be the same probability of success each time. So each trial. That goes along with your independence, right? If they're independent of one another, they don't impact one another, so they would have the same probability each time. So for each trial, and that's represented as P equals whatever it equals. So for instance, in our basketball example, that was our 0.72. Okay, so this acronym here, this is BINS. So those are the conditions that we need to check for a binomial random variable. We check our BINS conditions: binary, independent, set number of trials, same probability of success. Okay, the other thing is let's take a look at this formula a little bit, because this formula is going to be on your formula chart. Some of you may prefer you can use this formula in your calculator, or there's another way you can do it in your calculator. So it'll kind of be up to you what you chose. So our probability that X equals K, okay, and K is going to be our number of successes. And so when we look at our formula here, this formula looks like this, and then to the K power, and then times 1 minus P to the N minus K. Okay, so again, this is the big capital C right here. So I know this looks a little crazy, okay, but if we know what all these things mean, right? N is my set number of trials. So I'm going to do our basketball example down below it here, right? So 3, and then our C. K is going to be our number of successes. So in this case, let's say we wanted the probability that he made 2 and missed 1. Okay, so that would be our 2 there. Okay, and then P is our probability of success, as part of our conditions there, that S. So probability of success. So in our basketball example, it was 0.72. Again, with K being the same, right? This is our number of successes. So let's say he made 2 of those. 1 minus P is our probability of failure. So this parentheses there is our probability of failure, which is his 0.28 that he would miss it. N minus K is the number of failures. So out of his 3, he had 2 successes, therefore he would have had 1 failure. So you can put this into your calculator. If you go to your calculator and you're going to press math, arrow over to probability or prob, arrow down to number 3, which is the NCR. And then it will show up where you can put it into your calculator. And once you type in like the 3 and then the C is already there for you. It jumps right to the 2. You'll need to hit the arrow one more time to be able to bring it back up to a normal, not a subscript, to be able to put the 0.72. And you'll see that you'll get the same answer as you did on the first page there. Right, so looking at these conditions here for these particular problems, you're asked to determine whether it's a binomial distribution and to justify your answer. Justifying your answer here would come from explaining those bins conditions. So with context, that kind of thing. So ideally, go ahead and pause it, attempt to do these, and then come back and check your answers. Okay, so I'm going to shortcut just a little bit so that so that it won't be quite so messy for you, but I'm definitely going to say all the things. So make sure you're writing down what would truly get you full credit. So I need to be checking my bins here. So the first part I need to check is that binary. So when you are justifying with this, you need to define what a success is. So a success is an actual whacking of the mole, where a failure would be that you miss the mole or there's no whack, but you have to define those. So make sure you don't leave that out. Don't just say, yes, there's success. No, there's, and there's failure. Okay, for my independence, you're going to need to state that all the trials are independent, that one trial does not affect the other. Okay, for my set number of trials, I'm going to go ahead and I'm going to say there's a set number of trials, and I'm going to go ahead and list what that value is. Same for my S with my same probability. I want to actually define that probability of success as 0.8. So this meets all of those conditions. It has a set number of trials, a set probability, their trials are independent, and it has success or failure for each trial. So yes, this would be a binomial. So the second one for skee ball, again, for my binary, I'm going to define what a success is and what a failure is. So a success is the ball went in the 10,000 point hole. Failure is it did not. So make sure, again, you list those and define those. Independence, every time you throw the ball, it's independent of your other throws. Your set number of trials, there is none, right? It says until you get one in the hole. So that would be what's called a geometric, and we will do those next time. Okay, and then your set probability, that is the same actually. We've got a p equals 0.10, but it is not a binomial because it does not have a set number of trials. So looking at our last one here, explaining why. So again, our binary, define your success, define your failure. Success, the duck has a star. Failure, no star. Again, don't abbreviate as much as I am. Okay. Your independence, each trial is independent, mainly because the duck is replaced. If the duck wasn't replaced, then we'd have to check another condition that we'll get to later. Okay. But because each duck is replaced, each trial is independent. We do have a set number of trials at 10, and we have a set probability of success of p equals 0.2 of getting a duck that has a star. So that is a yes. And then my probability that I would win exactly 3 times. I'm going to come over here and do this off on the side so I have a bit more room. So my probability that W equals 3. Okay, so using my formula that I had before, right? My set number of trials is 10. C. My number of successes is 3 because I wanted the probability that I had 3 successes. My probability of success is 0.2 to the third power because I had 3 successes. My probability of failure then is 0.8. If I'm doing that, I'm going to have 7 failures. Okay, and when I punch that into my calculator, I get 0.2013. We can also use a distribution in our calculator, which I'll just go back and show you in class because I think that will be easier. All right, so let's look at this next one here. So looking at this quiz, go ahead and mark what you think your answers were for this quiz. And yes, you are correct. There are no questions. All right, so we could go through and mark this quiz, and I'm going to tell you that the right answers are A, B, B, D, and A. So you can make note of however many you got correct. Okay, and so let's define x here. X is the number of correct guesses. Is this a binomial setting? Explain. So I need to go through and I need to check my conditions, right? I need to determine if it's binary. I need to define my success, which would be a correct answer. Again, don't write an S. You need to write the word success, right? A failure would be an incorrect answer. So we need to define those so it meets that conditions. Are they independent? Is each trial independent of the other? So basically, is number one independent of number two? Yes, it is. Okay, each answer doesn't affect the other. Do I have a set number of trials? Yes, I have 5. Right, I had 5 trials that I had there. And do I have the same probability of success every time? Well, my probability of getting a right answer every single time is 0.25 because there are 4 answer choices there. So now I'm asked to calculate the probability of getting exactly 2 correct, right? So the probability that x, because I defined x as my number of guesses, so the probability that x equals 2. So again, my formula, I had 5 trials, C, 2 are correct. My probability of getting them correct is 0.25 to the second power because that's how many successes I had. So my probability of failure is 0.75. My probability, and then I would have had 3 failures because I only got 2 correct. Right? So when I plug that in my calculator, I get 0.264. All right, so now we're going to fill in the probability of getting x correct. We already did 2, right? 2 is 0.264. And then ideally, you need to be able to do all of these by yourself. Remember, this is our formula. Sorry, 1 minus p times n minus k to the n minus k power. So you should be able to do all of these yourself, right? So 5, C, I had 0 successes. So my probability is 0.25 to the 0, and then 0.75 to the 5. When I type that into my calculator, you should get 0.237. Take a minute and make sure you can do this. If you cannot do this, there's going to be simple questions and stuff that you're getting wrong. Pause it, try to do 1, 3, 4, 5, okay, and then come back and check your answers. Okay, so now you're asked to find and interpret the mean of the distribution and show your work. If you remember the mean of a distribution like this, right, this is what our formula looked like. The data point times the probability of that data point, and we add all those together, right? So we'd have 0 times 0.237 plus 1 times 0.396 plus 1, 2, 3 dots plus the last one. That counts as showing your work, right? When I do that, that gives me 1.25. But we already determined this is a binomial. So when it's a binomial, your mean of x, whoa, that was a mess. Your mean of x is equal to n times p. So in this case, my n is 0.25. I'm sorry, my p is 0.25. My n is 5. When I multiply those, I get the same thing. So with the binomial distribution, you can use the n times p formula. That's going to be a takeaway in case you're not catching on to that. Right, so for our standard deviation, again, for a binomial, our standard deviation is going to be, I can calculate that a little bit easier. That will be my standard deviation formula for a binomial. So in this case, it would be the square root of n, which was 5, times 0.25, probability of failure, 0.75. which will give me a standard deviation of 0.968. These are not complete answers because we did not interpret either one of them. So let's talk about what interpretation for this would look like. I don't think I'm going to try to write it up there because it's going to be super messy. So listen, pause, rewind as you need. So your interpretation of your mean, right? After many, many quizzes, the average score on the quiz is 1.25 correct out of 5. So you'll notice what was a little bit different with our interpretation stem there is we needed to say our number of trials. So after many, many quizzes, the average score on the quiz, so we're using our context, is 1.25 correct out of 5. And we will do a stem on the takeaway page in a minute. So then our standard deviation interpretation is, again, similar to what it was before. So the number correct on the quiz out of 5, that's where it becomes a little bit different, right? So then using our context, the number of correct answers on the quiz out of 5 typically varies by 0.968 correct from the mean of 0.25 correct. So that's going to, like I said, vary just a little bit from our traditional stem by including the number of trials in it. And we'll put this again on our takeaway page. So the probability of getting at most 3 correct. So our probability of X, and you'll notice it said at most. So I could get 0 correct, 1 correct, 2 correct, or 3 correct. So since I have this handy dandy probability distribution up there, I can just add those together, right? This is an or situation. I don't care which one it is, this, or this, right? So I can add all those together and I can get 0.985. Again, there is a way I can do this in the calculator as well, and I will show you how to do that in class where you can see that a little bit better. So leave some room on these pages so you can add it. Okay, so what about the probability of getting 3 or more correct? So you need to be comfortable writing these probability statements out, right? You'll notice it's a greater than or equal to because it said 3 or more. It didn't say more than 3. It included 3 in there. So I need to include 3, right? So I can add all of these up here, including my 3, my probability of getting 4, my probability of getting 5, add them all up, and I get 0.104 correct. Okay, and again, like I said, we'll show you how to do it in your calculator. All right, so let's look in our big idea box here that you have on the back. So some things would be if you are asked to describe a binomial, the things that you would use to describe it. So if you're asked to describe a binomial distribution, we leave this word off a lot, but it's a pretty important one. Okay, so you can use your bins to describe it. You know, describe your binary, your independence, your number of trials, your same probability. So you can use bins to describe it. You can describe the shape of the probability, and you can do that by making a histogram of the probability distribution itself. So a histogram of that probability distribution, so of that table that we made on the last slide. We'll do an example with this in just a minute as well. For center, you would describe mean, because you can calculate mean, right? We can do mean with n times p, right? And for that variability or spread, we're going to be using standard deviation because, again, I have a formula for standard deviation for this as well. So speaking of which, let's look at those, right? Again, in particular for a binomial only, right? If it fits our criteria, our mean formula is n times p, right? So after, here's your stem, I can't spell. Many trials. The average, we let them know we know it's an average number of successes in context, right? So all this should be in context. Number of successes in context is whatever that value that we calculated out of n. So that's kind of a basic sentence stem for you there. Same with standard deviation for this. So standard deviation, remember, whoa, that was a weird looking sigma there. So our standard deviation formula, right? N times P times 1 minus B, okay? And then again, our stem, the number of successes, again, in context. Typically varies by whatever that standard deviation is that you calculated from the mean of whatever that value is that you calculated out of n number of trials. And you can rearrange that just a little bit. You can put the n trials up in the context, right? The number of successes out of n number of trials typically varies by the standard deviation from the mean of whatever it is. But those are the things that must be included there when you're interpreting a standard deviation of a binomial. Okay, so ideally you pause and then come back and check your answers so that you can see how you're doing as you move through these. Okay, so does this setting represent a binomial distribution? Again, I'm not going to write everything out. Binary, define your success, define your failure. Yes, there is success and failure. There's no in between. Okay, trials being independent. So those trials are independent of one another. I do have a set number of trials at 10, and I do have the same probability for success all the way through at 0.25. So yes, this is a binomial distribution. It tells you to use technology here to make your probability distribution of y and describe its shape. I'm going to kind of lay out what this should be. I'm going to expect you are going to need to be able to do this. Okay, so again, if I'm doing the probability distribution, my probability is going to go over here on my y-axis. Okay, my number of successes is going to go down here on the bottom axis, the x-axis there. Okay, so in this case, I pulled 10 slips of paper out of the box. Yeah, I pulled it. I did it. Oh, the process was done 10 times. Okay, yeah, 4, 5, 6, 7, 8, 9, 10. Okay, my probability distribution. Let's see, let's return to the box. Mix well, acid to do it. Yeah. Okay, so I'm going to need to go ahead and I'm going to calculate this using that formula, right? So I have 10 trials. C, I pull out 0 wrinkles, pieces of paper. My probability of success is 0.25. I pulled out, I did that 10 times, and I get a value of, it's about, I don't remember off the top of my head, it's about 0.056. That needed to be a little bit taller. Oh well. So for 0, 2, 4, 6, 8. Okay, so I'm just graphing the probability here. So I would do this for 1. Again, you find this in your calculator under math, probability, and then you'll see it. Again, this is approximately 0.18 something. So I'm going to go through and draw this histogram. Whoops. So you need to draw that whole, you would go through and you would calculate that whole histogram and you would describe its shape, and it should be a little bit skewed to the right. Okay. Again, you want to be able to calculate those yourself. So I calculate and interpret the mean of y. So because it is a binomial, I can use my n times p. So 10 times 0.25, my mean is 2.5. It told me to interpret. I need to write the interpretation. After many, many sets of 10 drawings, right? So I got my 10 drawings in there. So after many, many sets of 10 drawings, the average number of crinkled papers drawn is 2.5. Again, I can tweak a little bit if we're strictly going from the stem. After many, many trials, the average number of papers pulled out, crinkled papers pulled out of 10 trials, the number of crinkled papers pulled is 2.5 out of 10. So again, after many, many trials, the average number of crinkled papers pulled is 2.5 out of 10. So my standard deviation, again, it's a binomial. Therefore, I can use this formula of, it's a minus. So 10 times 0.25 times 0.75, square root it all, and I get 1.369 is my standard deviation. Again, it asks me to interpret. So using my sentence stem, the number of crinkled papers pulled typically varies by 1.369 from the mean of 2.5 out of 10 trials, or the number of crinkled papers pulled out of 10 trials typically varies by 1.369 from the mean of 2.5. Okay, but make sure you include your interpretations. Okay, so I just wrote all this and none of it recorded. So I'm going to take a different color, point some stuff out. Please pay attention. Don't just blindly write, right? The stuff isn't going anywhere and you can pause it very easily. So if we look at the first one, is this a binomial setting? Explain. So I check my bends, right? I check my B. I name my successes and failures. I get a green. I do not get a green. That is met. It's a binary function. I check my independence. Independence is actually not met here. I am sampling without replacement. I pulled all 5 Skittles at one time. So that affects my independence here. I did not pull one, put it back, mix them up, pull another one. So officially this is not independent. I do have a set number of trials at 5 because I pulled 5 Skittles. And I have a set probability here of 0.2. Assuming that the Skittles are evenly distributed at 5 different flavors, 20% of them are going to be one flavor. So let's go ahead and find the probability of getting 5 green Skittles if this is not a binomial setting. So the probability of getting all 5 to be green, right? Initially, before I grabbed any of them, I had 2,000 green and I had 10,000 Skittles. Then I grabbed one, so now I have 9,000 Skittles, and I got a green one, so now I have 1,999 green Skittles. And now I have 9,998 Skittles, 1,998 green ones, and so on as I pull Skittle number 4 and Skittle number 5. And this gives me a probability of 0.00319. So now if I figure out the probability that all 5 are going to be green, and I assume this is a binomial, well, using my formula, I had 5 trials, I had 5 successes. My probability of success is 0.2. All 5 of those were successful. Probability of failure is 0.8 and 0. That's a 0, not a 6 or anything weird. 0 of them were successful. Okay, I had 0 failures. So when I put that formula in my calculator, I end up getting a probability that is about the same between the two. So when we go down to number 4 here, how do your answers from number 2 and number 3 compare? And why do you think this is? So they're about the same. And this is going to be due to the fact that our sample, okay, which is represented by a little n here, our sample is small relative to our population. Okay, so me pulling 1 or 2 Skittles out of a population of 10,000 just doesn't really and truly just doesn't make a big difference. Okay, and so that's why I can use what's called our 10% condition. So our 10% condition is used when independence is not met. So you'll see, I've dropped my arrow over here, right? So if independence is not met, so maybe I'm sampling without replacement, then I need to test my 10% condition. And if that's met, I can assume this is a binomial. So my 10% condition states that my sample size, so lowercase n, is less than or equal to 10% of my population size. Well, if my sample size here was 5, that is definitely less than 10% of my population size, which it would be all the Skittles. So I can assume this is a binomial distribution. Okay, so now let's look at a slightly different scenario. So in this scenario, Mr. Wilcox now grabs a huge handful of 100 Skittles from the large bin of 10,000 Skittles. Let X equal the green number of Skittles in a handful of 100 Skittles. X can be considered a binomial random variable because the 10% condition is satisfied, right? Because my sample size of 100 is still less than 10% here of my population. So what's the probability of getting at most 11 green Skittles? So when I write my probability statement here, right, at most, so that includes the number 11, okay? And I'm going to go ahead and, I know I've been telling you I'm going to show you how to do this on your calculator, but I'm going to try to show you right now. So you're going to go into your calculator, and in that distribution where we have found normal CDF and what have you, you're going to see oops, I'm so used to writing bio. You're going to see a binomial CDF and a binomial PDF. So again, go into that second vars, that distribution, okay, and you're going to want the CDF one, okay, and you're going to type in N, it's going to be 100, right, because that was my number of trials, right? I had N Skittles. My probability is 0.2, and my X value here is 11. And I'm going to hit enter, and that's going to give me 0.0126. So let's talk about your calculator for 1 second. So a couple things when using this on your calculator. So the calculator, like the normal distribution curve, the calculator only shows you what's to the left, right? That's why it was okay for 11, at most 11, because it's showing me this probability here. Remember, probability is the area underneath my curve. So I use the binomial CDF when it is a less than or equal to, a less than, a greater than or equal to. I use the PDF, so the binomial PDF, if it is an equal. I think of the P as perfect, right? So we had an example a few times ago where it said the probability of getting exactly 3. Well, then I would use the binomial PDF. In this case, I had a less than or equal sign, so I used the 11. So I used the CDF. But again, remember, it only shows me what is the probability to the left. So if it had said greater than or equal to or greater than 11, so if it had wanted this side, I would have needed to do 1 minus binomial CDF. Gosh, I hate this pen. Okay. Again, we'll go back in class and look at those examples and double check doing them on the calculator. But I just wanted to show it to you real quick right now. One, because this gets too crazy like if we don't start using our calculator pretty soon. Okay, so it gives us 0.0126. So we look at, this is our probability distribution right here. So the approximately shape of the distribution right here is, it is approximately normal. Okay, and so we calculate the mean and the standard deviation here. So our mean is 100 times 0.2, which gives us 20. Our standard deviation is our square root of 100 times 0.2 times 0.8, which gives us 4. So if I came over here and labeled my curve, right, I would label it 20 and 4. Okay, and now I could redo problem number 5. So this one up here with the probability that x is less than 11 using a normal distribution. Okay, so if if you like table A, feel free to use table A. I know most of you are normal CDF kind of people, right? So remembering how we do this, right? Our lower would be a big giant number, infinity. Our upper in this case is gonna be 11. Okay, and our mean is 20, and our standard deviation is 4, which gives us a probability of 0.0122, which is relatively close. Golly, this got even worse now they switched computers, which is relatively close to what we calculated before. So we can assume a normal distribution with what's called our large counts condition. And this could be helpful for us later. So a normal distribution can be assumed if our large counts condition is met. Our large counts condition is that NP is greater than or equal to 10, and you must have both of them, that N minus 1 minus P is greater than or equal to 10. Basically, our number of successes is going to be greater than or equal to 10, and our number of failures is going to be greater than or equal to 10 as well, right? And our number of trials times our percentage of success, our number of trials times our percentage of failure. Okay, so let's see, number of trials is 100 times 0.2, and you'll need to show them this. You need to show them all of those steps right there to get credit. You've got to show both of these things to get credit, and you have to show it over here too. So 100 times 0.8, which is equal to 80, which is greater than or equal to 10. Again, you have to show both of those things to get credit there. So our takeaways here are going to be the 10% condition and large counts, when I can use them, that kind of thing. So our 10% condition is going to be, I use this if independence isn't met, right? So if your independence is not met, then I'm going to come and I'm going to check this, right? So if I'm taking a random sample without replacement, it's got to be a random sample. These conditions become really important as we move into next semester. So don't sell yourself short. Don't cut corners with these, right? I know it will seem tedious, but just keep plugging away with it. So random sample without replacement of size, whatever it n is, right? From a population of capital N, again, I can't spell. So from a population of capital N, I can use a binomial, so I can assume that binomial distribution. If my sample size is less than or equal to 10% of my population. Okay, and for our other big takeaway, that's going to be your large counts, which allows you to use that normal distribution. So again, remember, this stuff isn't going away. So this allows you to use a normal distribution if, right, to model your binomial, I drew a histogram before, right? But if I've met my large counts, I don't need to draw that histogram. I can just assume a normal distribution if, right, m times p is greater than or equal to 10, and remember, it's got to be both, n times 1 minus p is greater than or equal to 10. You need to show your work for both of them, right? This is my expected number of successes. And this right here would be my expected number of failures. So if my expected number of successes and failures are both greater than 10, then we are good to go. We're going to look at a few examples with these and we'll be all set. All right, so suppose that 65% of high school students eat breakfast before going to school. A random sample of 500 high school students were surveyed. X equals the number of high school students in a random sample of size 500 who eat breakfast before going to school. Explain why X can be modeled by a binomial distribution, even though the sample was selected without replacement. Sorry about that. So I go through and I define my things, right? So I do my bins. I define a success as somebody that ate breakfast. Again, you don't write an S and an F, right? You write success, you write failure. This is just getting messier and messier now that I've switched computers, so we're not going to make this a giant awfulness, right? So that is true, right? It is binary. I have success, I have failure. I do not have independence because it said right here, it is without replacement. So I do not meet that independence. Okay. However, this is where the big but comes into play, right? If I don't meet the independence, right, I can still check my 10% rule, and 500 is going to be less than 10% of all high school students, because that's what we're talking about here. So there are definitely way more than 5,000 high school students, wherever you're taking this from. Okay, so I've got 5,000 high school students. Officially, this would be in the world because it doesn't say where. Okay, so my 10% condition is met, so I can still use this as a binomial because my set number of trials is met at 500. Okay, and my same probability is the same every time of 0.65 probability that they ate breakfast, of having a success. So use a binomial distribution to estimate the probability that 300 or fewer. So my probability that X is less than or equal to 300, okay, before going to school. So I'm going to, my calculator again, binomial, again in that distribution where the normal CDF is. I'm going to use CDF because it's a less than or equal to sign. Okay, I'm going to include 300 in it. If it had just been a less than, I would not have included 300. I would have said 299 because 300 would not have been included. But it is, so I will include it. Okay, 0.65. I don't know what happened there. Okay, and my X value is 300. I show my work just like I would with a normal CDF situation, and I get 0.0113. Justify why X can be used as a normal distribution, can be approximated by a normal distribution. Well, being able to do the normal distribution is my large counts rule. I need to show my work for both of them. So 500 times 0.65 is equal to 325, which is definitely bigger than 10, as well as my failures. So n times 1 minus p. So that would be 500 times 0.35, which gives me 175, which is also greater than or equal to 10. So that's my justification that this can be approximated by a normal distribution. So if I'm going to use the normal distribution that to approximate to estimate the probability that 300 or fewer high schools, I'm going to draw my curve. I need to label my curve, which means I need a mean of 500 times 0.65. So I get a mean of 325. So I can use that to label part of my curve. I also need a standard deviation. Again, it's a binomial, so I can use my formula here of 500 times 0.65 times 0.35, which will give me a standard deviation of 10.665. So I can use that to finish labeling my curve. you can 325. If I think about what these would be, 300 is going to be way down here somewhere. Right, so there's 300. I can plug that into my calculator. Normal CDF. So our normal CDF with our lower is our giant number. Our upper is 300. Our mean at 325. Again, this counts as showing my work. Remember, 10.665 for my standard deviation. Close my parentheses. I get 0.00954. And in the world of statistics, that is close enough to this 0.0113. Again, that's why I can approximate or estimate my probability. So we'll be doing lots of practice with these, and we'll look at what are called geometrics, and we'll be done with probability.